A massive star core may remain stable for millions of years, then cross an invisible threshold and collapse in seconds. Current models can describe the compression itself, but the exact point where the core stops resisting gravity and enters irreversible failure remains unclear. The interior of a massive star exists in a balance between outward pressure and inward gravitational force. As nuclear fuel is consumed, that balance weakens, forcing the stellar core into progressively denser states that become increasingly unstable under their own mass. Gravity does not suddenly appear at the end of the star's life. The force has always been there, compressing the core continuously, yet the collapse does not begin immediately. Something inside the system appears capable of delaying catastrophic failure until a hidden boundary is crossed. The collapse cascade begins when the core can no longer generate enough internal pressure to counter compression. Density rises rapidly, temperatures surge, and the stellar interior may enter physical conditions where ordinary matter behaves in ways current models only partially describe. The expected assumption is that the transition toward collapse should be gradual and predictable. Instead, observations of supernova-triggering stars suggest the system can remain apparently stable until the final moments before catastrophic breakdown. That contradiction creates a deeper problem inside the mechanism itself. If the star is already approaching critical instability, why does the observable structure often show no clear external warning before collapse accelerates beyond recovery? The core collapse cascade may compress matter faster than energy can escape. Radiation becomes trapped, pressure relationships change violently, and the interior structure could reorganize faster than conventional equilibrium models can fully track. Current models indicate that once the collapse threshold is crossed, the process rapidly feeds itself. Compression increases gravitational intensity, stronger gravity drives further compression, and the core enters a runaway state that may no longer allow reversal. Yet the exact trigger remains uncertain. The unresolved question is not whether massive stars collapse, but why the transition from unstable equilibrium to irreversible failure appears so abrupt. Some models suggest the hidden threshold emerges from pressure loss deep inside the stellar core. As nuclear reactions weaken, the system may suddenly lose the internal resistance required to support its own mass, causing gravity to dominate almost instantly. Other interpretations imply the instability is tied to the structure of matter itself under extreme compression. The collapse may not begin because gravity becomes stronger, but because matter reaches conditions where known pressure support mechanisms stop functioning cleanly. Neither explanation fully resolves the anomaly. Both approaches describe how collapse accelerates after the threshold is crossed, but neither clearly identifies why the system can remain stable until the final boundary is reached. The observable pattern becomes even stranger during supernova initiation. A star that appeared structurally intact may suddenly release enormous amounts of energy, while the core itself disappears into a rapidly collapsing interior region. That visible explosion can create the illusion that the star is violently expanding outward. In reality, the explosion may be a consequence of inward collapse occurring faster than the surrounding stellar layers can respond coherently. This creates a physical contrast that current models still struggle to simplify cleanly. The outward supernova event is driven by an inward gravitational catastrophe hidden beneath the visible surface of the star. The deeper the collapse progresses, the more incomplete the known mechanisms become. Matter densities may approach conditions where existing models of pressure, particle interaction, and energy transport begin losing predictive certainty. The instability also unfolds on radically compressed timescales. Processes that required millions of years to evolve may terminate in seconds once the hidden threshold is crossed, suggesting the system contains a non-linear transition that remains poorly constrained. That non-linear behavior is difficult to observe directly because the critical stages occur deep inside opaque stellar interiors. Scientists can infer the collapse from radiation signatures and supernova remnants, but the exact internal sequence remains largely inaccessible. The observational gap matters because the unresolved mechanism sits at the most important point in the chain. Without direct access to the trigger phase, it becomes difficult to determine whether the collapse threshold is caused by energy transport failure, matter state instability, or an incomplete understanding of gravitational compression itself. Current models can reproduce many large-scale outcomes of stellar collapse. They can simulate compression, estimate supernova energy release, and predict remnant formation under certain conditions. But simulation agreement does not fully resolve the hidden transition problem. The models often depend on assumptions about internal behavior that cannot yet be directly verified under real stellar conditions. The collapse cascade, therefore, represents more than a violent astrophysical event. It exposes a boundary where known stellar physics begins transitioning from measurable behavior into partially inferred mechanisms. The contradiction becomes difficult to ignore. Massive stars appear governed by stable physical laws for most of their existence. Yet near the end of their life cycle, the system may cross an invisible point where those same laws stop predicting behavior cleanly. That unresolved boundary is what makes the collapse threshold fundamentally unstable as a scientific problem. The star does not simply explode. It appears to pass through a hidden state change that current models can describe mathematically, but still cannot fully explain physically. The deeper the investigation goes, the narrower the uncertainty becomes. The missing mechanism may exist within only a brief phase of collapse, yet that small, unresolved interval determines how an entire massive star transitions from equilibrium into irreversible destruction. By the time the observable supernova appears, the critical failure may have already occurred deep inside the core, long before any external signal becomes visible. Current observations reveal the aftermath of the collapse far more clearly than the hidden boundary that initiated it. As the collapse accelerates, the stellar core may shrink faster than surrounding layers can physically respond. The outer structure continues behaving as though equilibrium still exists, even while the interior has already entered irreversible failure. The observable supernova signal therefore arrives late relative to the core instability itself. By the time radiation escapes the outer layers, the hidden collapse process may already be far beyond recovery. This delay creates a severe observational constraint. Scientists can detect the explosion, measure the expanding debris, and estimate the energy release. But the critical transition phase remains buried inside the star during the most violent stage of compression. The deeper the core collapses, the more rapidly physical conditions intensify. Density, pressure, and gravitational confinement all increase together, tightening the system toward regions where known equations become increasingly difficult to stabilize consistently. Some collapse models begin diverging sharply under these conditions. Small differences in assumptions about pressure transport or internal compression can produce radically different collapse outcomes, suggesting the threshold behavior itself may be highly sensitive to hidden dependencies. That sensitivity should not exist so close to a supposedly deterministic gravitational process. Gravity appears universal and predictable on large scales, yet near the collapse boundary, the system may become extremely unstable to microscopic internal conditions. The visible structure of the star can still appear relatively coherent during this stage. The catastrophic instability remains concentrated inside the core, hidden beneath layers that temporarily preserve the appearance of normal stellar behavior. Then the propagation accelerates. The collapse cascade may move inward and outward simultaneously through different physical pathways. The core contracts under gravity, while shock behavior begins transmitting instability back into the surrounding stellar structure, amplifying the disruption across the star. Current models indicate that once compression exceeds certain limits, the core may lose the ability to redistribute pressure efficiently. Instead of stabilizing local instabilities, the system begins amplifying them faster than internal equilibrium can recover. That amplification creates another unresolved boundary. The collapse no longer behaves like a slow gravitational adjustment. It begins resembling a runaway state transition where ordinary balancing mechanisms stop scaling cleanly. With increasing density, observationally, the event appears almost discontinuous. A massive star may transition from long-term equilibrium into catastrophic destruction on timescales that seem disproportionately short compared to the duration of its stable existence. The imbalance becomes difficult to reconcile physically. Millions of years of stellar stability may depend on mechanisms that fail within seconds once compression crosses a hidden limit. Some interpretations suggest the instability threshold is not a single physical point, but a cascading dependency chain inside the collapsing core. Small failures in pressure support could propagate rapidly through adjacent regions, causing the entire structure to destabilize non-linearly. Other models imply the opposite problem. The collapse may remain locally stable for longer than expected, forcing the runaway transition to emerge only after multiple hidden constraints fail simultaneously. Neither interpretation fully explains the observable sharpness of the transition. Both approaches still struggle to determine why the collapse boundary appears so narrow between equilibrium and destruction. The observable radiation pattern only complicates the problem further. Supernova energy release suggests enormous internal restructuring, yet much of the decisive collapse process remains physically concealed from direct measurement. Scientists are effectively reconstructing the collapse backward from its aftermath. The visible explosion provides evidence that catastrophic compression occurred, but the mechanism governing the trigger threshold itself remains partially inferred rather than directly observed. This limitation propagates into every stage of the model. Uncertainty in the trigger phase affects estimates of collapse timing, instability growth, and the exact sequence through which the core loses structural resistance. The deeper the compression proceeds, the smaller the directly observable region becomes. The system generating the most important physical transition is also the part least accessible to observation. That observational asymmetry creates a persistent contradiction. The collapse cascade may be governed by internal mechanisms that current instruments cannot isolate cleanly, even though the external consequences are among the most energetic events ever observed in stellar systems. The anomaly, therefore, expands beyond the star itself. The unresolved threshold problem affects how scientists interpret the entire transition between stable stellar evolution and catastrophic gravitational failure. And the closer models move toward the exact collapse boundary, the less stable their explanations appear to become. Current models can describe many stages of stellar collapse with increasing precision. They can estimate compression rates, simulate shock propagation, and reproduce large-scale supernova behavior under controlled assumptions. But the most important transition inside the system still remains partially hidden. The exact moment where a massive star crosses from unstable equilibrium into irreversible collapse is not directly observable, and the mechanism governing that boundary remains incomplete. The collapse cascade therefore exposes more than a violent stellar event. It reveals a region where gravitational behavior appears physically consistent on large scales, while the internal trigger mechanism stops resolving cleanly under extreme compression. A massive star may spend millions of years resisting collapse, then lose that resistance almost instantly once a hidden threshold is crossed. Current physics can model the aftermath far more clearly than the boundary that initiates it. The observable explosion is not the deepest anomaly. The deeper anomaly is that the star appears to remain stable until the mechanism preventing collapse suddenly no longer works, and current models still cannot fully explain why that boundary exists where it does.